Hi everyone. So far we've been talking about relative dating in our previous videos. We've been comparing rock layers and in terms of younger versus older. And that's what we call relative dating. Today we're going to be focusing more on absolute dating. And absolute dating is finding the exact age of a fossil in numbers. So we're going to try to figure out what the exact ages of rock layers or fossils are. So, to do that, we need to talk about atoms. Remember, atoms are made up of or have electrons, protons, and neutrons. However, there are some atoms that are unstable atoms called isotopes. And the reason isotopes are unstable atoms is because isotopes are atoms that either have too many protons or too many neutrons. So, what these isotopes try to do, or unstable atoms try to do, is they try to become stable by getting rid of these protons or extra protons and extra neutrons. The thing is, when isotopes try to balance themselves out or become stable, by releasing these extra protons and neutrons, they're also releasing radiation. So that's why we call this radioactive decay. Decay means to turn stable. So when the isotopes are releasing extra protons and neutrons, they are decaying or turning stable. And we also call this radioactive decay because when an atom turns stable by releasing these extra protons and neutrons, they're also releasing radiation. This was optional for you to write this down, these definitions down in your notebook. So decay means to turn stable. Let's say I have a sample of radioactive elements, right? Radioactive isotopes, and all these isotopes want to turn stable. The thing is, we don't know when each individual isotope will turn stable. However, what we do know for most isotopes is how long it will take half of my sample to turn stable. So we call this a half life. Half life is the amount of time it takes for half of atoms in a sample of radioactive elements to decay into stable elements. Say I have a sample of unstable elements in red, and blue means they turn stable. This sample of red elements will take 10,000 years for half of my sample to turn stable, blue. It will take another 10,000 years for another half of my sample to turn stable, and then another 10,000 years for half of my leftover unstable atoms to turn stable, right? So I had four red atoms here that were unstable, half of it became stable, blue, and it took 10,000 years. And then another 10,000 years later, half of that sample will turn stable. So, what we call this is a half life. We know for this particular radioactive sample, half of my sample will turn stable in 10,000 years, and therefore the half life for my sample is 10,000 years. So, go to your reference table, page 1, and if you do, you'll find this chart called radioactive decay data. And what this is showing you is a radioactive isotope. A radioactive isotope is an unstable atom that is radioactive. So we have carbon 14 that is radioactive, potassium 40, uranium 238, rubidium 87. These are all radioactive isotopes that want to become stable. Now, the second column shows the disintegration product, meaning what element the unstable atom turns into when it becomes stable. For instance, carbon 14 is unstable. When it becomes stable, it turns into nitrogen 14. So, in my previous example, remember red was unstable and blue was stable. In this case, all these red samples or atoms are carbon 14, they're all unstable. And for carbon 14, when it becomes stable, when half of it becomes stable, blue, that blue is actually nitrogen 14, the stable version of carbon 14 when it loses a proton. So that's what we mean by disintegration product, the blue, the product that forms that's stable. Finally, the last column shows the half life. How long does it take for half of my sample to become stable? For instance, if I have a sample of carbon 14, red, it will take half of the carbon 14 to turn into blue, nitrogen 14, my stable disintegration product, and it will take 5.7 times 10 to the 3, or 5,700 years, which these two are the same thing. So it will take 5,700 years for half of my carbon 14 sample, which is unstable, to become stable nitrogen 14. It will take another 5.7 times 10 to the 3, or 5,700 years, for half of the rest of my unstable carbon 14 to become stable. It will take another 5,700 years for half of the rest of my carbon 14 to turn stable, and then another 5,700 years, and so on. That's why we call this the carbon 14's half life, because for carbon 14 specifically, half of the sample will turn into stable nitrogen 14 atoms in 5,700 years. Notice different radioactive isotopes have different half lives. It takes a longer amount of time for half of potassium 40 to turn into argon and calcium. It takes even longer amount of time for half of uranium 238 or a sample of uranium 38 to turn into Pb or lead 206, and so on. So here's another example. Say I have a carbon 14 in blue, right? These are all carbon 14. Carbon 14, right now I have zero half lives. I have 100% carbon 14 and zero nitrogen 14. But after one half life, or 5,700 years later, half of my sample will turn into a stable nitrogen 14. Now I have 50% carbon 14, 50% nitrogen 14. Another 5,700 years later, half of what I have left over, half of the leftover carbon 14 will turn into nitrogen 14. Now I have 25% carbon 14 left and 75% nitrogen 14, my disintegration product. Finally, now I have this much carbon 14 left. Another half life later, or 5,700 years later, half of these carbon 14s will turn into nitrogen 14. Now I have 12.5% of carbon 14 left after three half lives, and 87.5% nitrogen 14 left after three half lives. So, what you should notice is over time, over the different half lives, my carbon 14 is decreasing. If you drew a graph, it would look like a downwards curve. But you should also notice that over the different half lives, my nitrogen 14 is increasing. So my radioactive isotope, the amount is decreasing exponentially, but my disintegration product, in this case nitrogen 14, is increasing exponentially. So what a normal graph for radioactive isotopes and their decay products or disintegration products looks like is something like this. The radioactive element, in this case carbon 14, is decreasing in a curve shape exponentially, and its disintegration product, nitrogen 14 in this case, will increase exponentially at the same time, kind of like this. This is another example of a potassium 40. As potassium 40 decreases, my radioactive isotope, it will turn into argon 40 and calcium 40, and those disintegration products should increase. And carbon 14 takes 1.3 times 10 to the power 9th years for one half life, for half of my sample to turn stable. So the thing is, all living organisms have carbon, okay? And all living organisms absorb carbon 14 from the atmosphere. But when they die, they're no longer absorbing carbon 14, so that carbon 14 starts to decay into nitrogen 14. And if we find a bone of an ancient fossil, and that fossil had carbon 14, and we see a ratio of a certain amount of carbon 14 versus nitrogen 14, we can figure out how many half lives that fossil went through, and therefore figure out the age of that fossil. If I find a fossil and it has 12.5% carbon 14 and 87.5% nitrogen 14, I know that sample went through three half lives, and I know how long three half lives take for carbon 14, and that's how I can figure out how old that fossil is. The thing is, carbon 14's half life is very short, only 5,700 years. That means after around 20,000 or to 30,000 years or so, we're going to run out of carbon 14. If my carbon 14 just keeps having and having and having, we're going to run out soon, right? So, since carbon 14 has such a short half life, it's really hard to use carbon 14 to date very, very old fossils, specifically fossils that are more than 1 million years old. We can really only use carbon 14 to date fossils that are less than 1 million years old. So really, one popular question that you'll see on the regions is, how come we can only use mostly date fossils like mastodons by using carbon 14? This is a mastodon. Its symbol is O. And notice O only lived or existed around 0.01 million years ago. zero point zero 0.01 million is 10,000 years ago. So that's why carbon 14 can be used to date a mastodon, because carbon 14's half-life is short enough to date a mastodon. Carbon 14 can be used to date items that are less than a million years old, not more than that. So that's why we can't really use carbon 14 to date dinosaurs, L, because those dinosaurs are around more than 200 million years old. We cannot use carbon 14 to date fossils more than 1 million years old. So go ahead and open your note packet and write this down. Carbon 14 can only date younger fossils like mastodons because carbon 14 has a short half life. And anytime you're asked about why carbon 14 can be used to date younger fossils only, why can't we use carbon 14 to date much older fossils, the answer should be carbon 14 just has a short half life. We use radioactive isotopes like potassium 40, uranium 238, and rubidium 87 with longer half lives to date much older fossils. So, in the next video, we're going to do some practice questions. But for now, that's it.